This is part 1 of theme 8. We kick off theme 8 with the fundamental theorem of calculus. This theorem truly is of fundamental importance to your maths education, and therefore we look at the proof of this theorem in a very careful and thorough manner. The fundamental theorem of calculus has got two parts. This is part 1, where we are going to show the relation between the first use of squiggly sign as a signed area and the second use of squiggly sign as an antiderivative function. At first sight, this doesn't seem to make sense because like for example, let's be concrete. Let's say that our function is our y equals x with domain 0, 3. So this was the function that was modeling our isosceles triangle of 3 by 3. Then 0, 3 of this function actually gave you a number, and that number was the signed area underneath f to the x-axis from x equals 0 and x equals 3. Okay, so this one actually gave you a number, and it was a geometric concept because you could you visualize it as a signed area. Okay, so in this case it was just from x equals 0 to x equals 3, and then it was this area. Okay, so it was a geometric concept. Okay, now on the other hand, the second use of squiggly sign, where there were no numbers, of this function actually gave us a function, and that function had the special property that when you differentiate it, it gives you precisely this guy, the integrand. So in this case it was x squared upon 2. And then we then added on a constant of integration because all of them all had this format. So C could be any real number, any. Okay, it could be a million, it could be 10,000, it could be minus 6 billion, even as small as minus 1 times 10 to the minus 100. It could be any real number. Okay, good. Now, what the fundamental theorem of calculus does is that it relates this geometric and this algebraic concept as follows. So in order to explain how the relation goes, which doesn't seem to make sense because one of them just gives you a number and the other one gives you a function. But in order to explain how the fundamental theorem of calculus works, and what I'm going to do now is that I'm going to introduce to you the idea of what is called a partial area function. Okay, so let's actually call it big f of x to keep it different from our normal f of x equals x whose domain is equal to 0, 3. Okay, so what do I mean by a partial area function? Okay, now this partial area function is going to be constructed from our starting function. Okay, so it's going to be constructed from our starting function f of x equals x, where the domain is 0 to 3. Okay, now this new function that we are going to build from our starting function, which is modeling the isosceles triangle of 3 by 3, this function will share the domain identically. So the two domains are going to be identical. Okay, right. So let's see. So therefore, let's see how we define this new function, capital F, at different x's between 0 to 3. And this is how we are going to define it, okay? So let's look at our original function. Our original function is this 45-degree line, y equals x, which models the 3 by 3 isosceles triangle. And the domain is going to be from x equals 0 to x equals 3. Now, I'm going to make another function. And so this is f of x, okay? Y equals f of x equals x. This is the picture of y equals f of x equals x, okay? Now, I'm now going to show you how big f of x looks like, okay? How to define big f of x. Okay, I'm going to show you how to define big f of x for exactly the same domain. So this means x equals 0 to x equals 3, right? Now, how I'm going to define it is as follows, okay? So let's pick, so you will ask me, how does this new function behave at x equals 1? Because 1 is in the domain 0, 3, okay? Well, to calculate what this f at 1 is, what I do here is that I actually calculate the signed area starting from 0 up to 1, okay? So what I do here is that I actually, so this is what's going on, 0 to 1, and then I calculate just this signed area from 0 to 1, okay? So in this case, okay, this guy is an isosceles triangle of base height 1. So therefore, it's half base times height, which is 1 times 1, and so the answer is going to be a half. So at x equals 1, I should end up with the value of a half, okay? So this is how my function value gives. So it gives me, so geometrically, f at 1 gives me the partial area. So it doesn't give me the total area from 0 to 3. It gives me the partial area starting from x equals 0, only up to x equals 1, okay? And why 1? Because that is how the function behaves, okay? Now, what about how does f behave at 2? Okay, so once again, this will give me the partial area starting from x equals 0 all the way up to x equals 2. So if I calculate this partial area all the way from x equals 0 to x equals 2, notice that it's a bigger area because it's a bigger isosceles triangle. So it's going to be 0 to 2. And so therefore, I'll get a bigger y value, which is in this case 2. So at 2, I end up with the value 2. Get it? Okay. Right. Okay. So, and then let's find f at 3. Well, f at 3 is the partial area starting from x0 up to x equals 3. Okay. And so therefore now at x equals 3, this now gives you the total area underneath the curve. And we know that from experience, it turned out to be 9 upon 2, which is 4.5, which is going to be 4.5 right up here. And f at 0, notice that f at 0, this will give me the area starting from 0 up to 0. And so obviously this is equal to 0. And so what I end up with is, I end up with a new function called big F, and it looks like this. There it goes. See? So it's not even a straight line. So this is what is called a partial area function. All right? Now, so this is how we define the partial area function. So it has exactly the same domain as the original function. And what it does, it spits out the partial area starting from a up to x. Okay? Right. Now, so having carefully explained what a partial area function is, let me now give you the statement, what the fundamental theorem of calculus says. Okay, now it says that if, okay, and this is a big if f is continuous, so remember on 0, 3, okay, I'm going to set it on a I'm going to just be concrete here. So if f is continuous on 0, 3, okay, okay, so this is what is called the very, very important qualifier. Okay, so the function has to be nice. Okay, so in this case, f must be a what? It must be a friendly function. So remember that we are calling continuous functions friendly. Remember, the function doesn't have to be differentiable. All it needs to be is friendly. So if f is actually continuous on 0, 3, okay, then this partial area function f of x, which gives me all the partial areas from 0 up to x. Okay, now let's be careful. Now notice that, you see, I'm changing the t into, instead of using f of x, I'm now using the symbol t. Why? Because I'm trying to avoid notational clash, because here the x is in fact the constant, is a constant. We are finding the area from 0 up to x, where x is any fixed number between 0 to 3. Okay, so notice that this big F has exactly the same domain as your original little f. Okay, then the point here is that so if f is little f is so if I have a function that is continuous on 0, 3, then I can construct its partial area function. Let's call big F the partial area function. And what I know about this partial area function is that if I differentiate this partial area function, I will always get f. Okay, so in other words, this partial area function f of x is a special type of let us call it a particular case of a antiderivative of f of x. Okay, so in other case, our f of x was equal to x. Now this function that we constructed just a few minutes ago as follows with all these partial area functions. Okay, what I know is that if I differentiate him, I will always get x out. Okay, and this is what the fundamental theorem of calculus says. But okay, so so this guy, so in your textbooks they write it out in full. If I differentiate the integral, okay, so this is the partial area function which gives me the signed area starting from 0 to x. Okay, so this is my partial area function. That's my partial area function. If I differentiate this partial area function, this partial area function is an antiderivative of f. So therefore, if I differentiate this partial area function, I will in fact get f. And this is true for all x in my domain 0, 3. Okay? Right. Okay. So okay, so let's look at, okay, so let's actually look at, before we actually do the proof of why the partial area function, why it is an antiderivative, is that let's actually see some of the why this thing is so powerful. The reason why this fundamental theorem of calculus part 1 is so powerful is because it shows that the first thing is that integration, which in our case we mean the definite integration, okay, the definite integral, has what is called a smoothing effect. So what it does is that it takes a function f of x, okay, so let's look at this. It takes this function f of x. Now this guy, remember, he's just only friendly, okay, in that he's only continuous on this domain 0, 3. It doesn't have to be nice, okay. Friendly people are not necessarily nice, okay. Nice is when you actually have the function having derivatives everywhere. So for example, let me give you an example of someone that's friendly but not nice, okay. An example of this is f of x. Okay, let's start. F of x is equal to the absolute value of x, where my domain is -1 and 1. So this is my V shape. You see, it's sharp. You see, so this is at -1 and 1. Now this function is continuous everywhere, but he is not nice because he's not differentiable everywhere. The problem happens here at this sharp point 0. That's where the problem happens here. So, at this point, at this sharp point, this function doesn't behave nicely. Okay. So this function is an example of a friendly function that is not nice, right? Okay. So what happens here is that if I take just a friendly function f of x, and then I use I actually use the definite integral to make to construct from 0 to x. So what I then do is I then construct a new function, exactly the same domain, okay, exactly the same domain, okay. Now when I create this function f of x, so how did I create it? I just created, you see, it's the same. I just took f and all I did was just calculate the area starting from 0 up to x. So notice, you see, because of this notational clash, I'm just going to change this thing to t, okay, that's all. So notice that in this case, when I made this new function, what happened here was that I ended up with this function now is nice. I mean, now this guy is a nice function because the function is differentiable everywhere. Is differentiable everywhere, and the derivative of the function is precisely the friendly function f of x, okay. So what integration does is that it takes your original function who is only friendly, and then he converts it into a nice function, okay. So let's okay, so this smoothing effect, okay, so let's now actually look at the proof. So what do we have to prove is that I have to prove that if I differentiate this partial area function, I must get the integrand, the original integrand function f of x, okay, where all I know is that f is just continuous. Okay, so let's actually prove this, and this must be true for all x's in 0 to 3. Okay, so let's actually prove this. Okay, So if I calculate his derivative, how do I calculate? So let's start from the left-hand side. The derivative of a function is done in two steps. First, I must take the difference quotient. So I must take f at h away, okay, minus f at x divided by h. Okay, this is my difference quotient. Then I must then take the limit as h approaches 0. Okay. So let's just focus on the difference quotient. Okay. Okay. So let's now calculate what is f of x plus h minus f of x divided by h. Okay. So remember, your x here is a constant. It is fixed. Okay. So f of x plus h, remember, this is the partial area function starting from the start a, or a equals 0 up to x plus h. Okay. This is to, you see, that's why I'm using t, simply to avoid clashing with the x here, minus the partial area function up to x of f, right? All over h. Okay, are we together? Now, do you still remember this is the additivity of the intervals? So here I'm finding the area from 0 up to x plus h, okay? And then I'm subtracting the partial area from 0 to x. Okay, so if you look at, so I'm going to, let's just call this guy the blue area. Okay, so the blue area is going to be all the way up to here. Let's call this the green area. Okay, and then the green area is going to be up to here. So I have to find their difference. So therefore, the difference of them is going to be x and x plus h. Okay, all over h. Right? Okay. So then what happens then here is that I can then write this guy out as 1 over h times the integral of x starting from, starting partial area from x to x plus h of my function. Okay. Now at this point, let's actually look at this guy very, very carefully. Okay. And let's look at what is the meaning of 1 over h. Okay. This 1 over h, that guy, is nothing but the length of the interval starting from x to x plus h. So this is the length of the base of your integral. Okay, and what is this one? So this is nothing but the signed area starting from x to x plus h, and to h is actually the length starting from x to x plus h. So so this therefore means that this is nothing but the average function value of f starting between x and x plus h. So this means that the difference quotient gives you the average function value between x and x plus h. Okay, so let's actually now, so this was what the difference quotient is. Therefore, remember, it's a two-step process. The derivative of my partial area function, I must now take the limit of my difference quotient. But who's my difference quotient? It is the average function value between x and x plus h. Okay. Now, what does the mean value theorem say? Okay, so in our previous video, we saw that the average function value between x and x plus h, this can be achieved by some function value that is by some y value that is somewhere in between, for some special x equals c, for some c where the c is somewhere in between x and x plus h. Okay, so because that's the domain now. Okay, so let's actually call this ch, because the ch. So in other words, by the mean value theorem, this average function value must be somewhere between there. And this is where, in order for this to be true, this is where you need the function to be continuous. You see? Because then and only then can you have this guarantee. So when this function is actually continuous, now remember that this c is actually stuck in between. Remember, x is a constant, this constant x value, fixed x value, and this value that's h plus a away, h away from x. Okay, so but notice that so here I've got x, okay, and x plus h, and then there is some ch here. But notice that when h becomes close to 0, x plus h approaches x, and this will force my ch to become close to x. Okay, so this means that my ch will actually approach x. Yeah, it's the same as the limit as ch approaches x of f of ch. And because f is continuous, the limit as ch approaches x is simply going to be f at x. Yeah, just the function value at the point of approach, which is x. Okay, so there we have it. So this is the proof of the fundamental theorem of calculus, and this brings us to the end of our video.